All right, everybody, we're going to go ahead and try to get started here. I've been having some technical difficulties for about 15 minutes now, and I don't really have much else time to figure this out. So we're going to do the best that we can. But we're going to look at 11.2, 11.3, where we have independent and dependent events, and then disjoint overlapping events, which we'll figure out shortly. So the key difference you want to know about our independent and dependent events is knowing that independent events basically occur without affecting another one. Dependent events happen basically dependent on something, right? So if one thing happens, then another thing happens. And so that's kind of the idea we want to go with there. Okay. And so we look at this bottom portion here, the probability that event B occurs given that event A has occurred is called the conditional probability. Okay, so it just basically means like because this thing happened, this is the likelihood that something else is going to happen. Okay, and we represent it as that. Okay, and I already give you an example of independent, right? If you flip a coin, a heads does not influence a tails, so that's not going to be the dependent. It's going to be independent. They're completely independent of each other. However, something that would be dependent would be an example for, let's say, our, oh, I don't know, like our cards, for example, right? So, example for dependent would be like, I don't know, getting an ace, we'll say. Yeah, I don't know why it's not getting an ace. I don't know why this is not getting an ace. There we go. Finally. Okay. And so this is going to be something that's going to be dependent, right? Because let's say first card was well, let's say it's another ace. So then second card, actually, sorry, we're gonna back up a little bit. Instead of say getting an ace for our dependent, we're gonna say picking two cards. And it'll be a little easier. So picking two cards. Then we'll say the first card was an ace. Then the second card could be literally anything else, right? So second is anything else. Okay. But if I pull the first ace, right, there's four aces in the deck of 52 cards. So I have a 4 and 52 chance of getting it, which is reducible or simplifiable. We can say that this is going to be equal to 1 over 13. However, if I take that ace out of the deck and I look to get literally any other card, let's say we're also looking for another ace. Well, I already took one ace out, so that influences to make it down 1, but I'm also influencing to go down to 51 cards. I no longer have 52 cards, so that's going to influence what is my possibility of getting another ace, or it influences the possibility of getting a 4 or anything else like that. So that's kind of what we're going to think about. And we have some examples. Okay, as a board game, as part of the board, you need to spin the spinner, which is divided into equal parts. Find the probability that you get a 5 on your first spin and a number greater than 3 on your second spin. Okay, now with this, for whatever reason, your notes does not really cover these different kinds of things very well. And by cover them very well, I mean like at all. Okay, so let's first annotate as much as we can. So when it says equal parts, we're going to say equal probability. Okay, equal probability. Then your first event is going to be getting a 5 on your first spin. So that is event 1. Then the second event is a number greater than 3 on the second spin. That's going to be event 2. And the first thing you want to figure out is this independent or is this dependent? Okay. Now, spinner, that's not taking out each piece. This is definitely going to be independent. Okay, one spin does not affect the other one. So we're going to write that. Independent. One spin does not affect a fraction e for e for well, you know what I'm trying to say. A fraction e for result. There you go. Okay. So one spin does not affect the other. Okay. And so because it's gonna have those like that, we understand this. We're actually going to write a little bit of different notation. And I meant to put this into your notes, but I completely forgot because I was running out of time apparently. And so here we are. But we're going to have P, A, and B. Okay. Where A and B is event 1 and event 2 respectively. Okay. And so whenever you're trying to find the probability of A and B, that's going to be the probability of A times the probability of B. Okay, and so this equation right here, I would definitely star this. That is something you should know. I think it's also on your reference sheet, and it is, yes, it is under probability on the second part of your reference sheet. I would star that just because anyway, because I think it's still good to know. But we have that. And so if we're looking for our probability of getting a 5, well, there's 8 equal pieces. There's only 8 possibilities here. And I know 5 is one of them, so 1 over 8 times getting a number greater than 3 on my second spin. That's going to be, well, greater than, so that's going to be 4, 5, 6, 7, and 8. That's 5 possibilities, so 5 over 8. And so I multiply across 5 over 64, or 7.8%. Okay. You do the same thing for the next one. You come on back. All right, we'll figure out what our first event is. Our first event is going to be getting an even number. So event 1. We'll call that A. Then event 2, called B. And we'll do the same thing because they're independent from each other. We can just do the same approach. So A and B equals the probability of A, which is 4 over 8, because we have evens and odds that are the same amount. Then we have a number less than 3, which is only going to be 1 and 2. So we're going to have 2 over 8. So for a grand total of 8 over 64, that's going to be 8, and that equals 12.5%. Okay. Nothing too difficult. A lot of this unit is going to be really just examples. And actually, I'm looking at my notes here. It's straight up just examples. So, just as much as we've done beforehand, like make sure that you're trying the notes on yourself or for yourself first. Okay, just like always. We'll go over to the next one. Here. It's doing that thing again. In the last video. I don't know why it's done. I don't know why it's doing this. It's a little annoying. Let's see. Fix it. Fix it. It would appear I cannot fix it, and this is quite agitating. I don't know why it's not doing the thing I want it to do. I just want to be able to change the color of this thing, but it's not letting me. Again, it's quite agitating. Okay, well, I guess we're gonna stick with this blue. Hope you like the color blue, because that's what's gonna have to happen. Unfortunately for us. No, my clicker's not working. Everything's just bad news bears today, I guess. All right, well, we'll work with what we got. Okay, so in this problem here, we have a bag that contains $20 bills, or sorry, $21 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside, and then randomly draw another bill in the bag. Well, find the probability that both events A and B will occur. So whenever you see the word both, okay, the word both should immediately make you think and. Okay, and multiplication. Okay. And so what I mean by and multiplication is we're going to do the same thing that we did in the previous problem, just a little bit different. Okay, just a little bit different. Okay, so we're still going to have this idea of, putting things together. However, in this problem, we need to figure out, is it dependent or is it independent? All right, if I pull a $1 bill from the bag and don't replace it, right? Because I'm not gonna put the dollar bill back in there. I'm gonna take the dollar bill, even if it's just $1. Does that affect the amount of bills that are still left in the bag? And that is gonna be a yes. So whenever you see this, both, right, word, you're gonna think and multiplication. So you're gonna still have probability of event A and the probability of event B like this. But your equation is going to slightly change because it is dependent. Okay. And the equation here is going to be probability of A times the probability of B with an absolute value bar. Think. Yep, absolute value bar. A, written just like this. Again, this is also on your spreadsheet, your reference sheet, so you should be fine without having to memorize that. But how this is going to work. Event A is pulling the first bill to be $100. Event B is the second bill to be $100. So what is the probability if I get a $100 bill on my first one? Well, there's 5 bills that are 100, and there's 25 total. I have 25 bills. Well, if I somehow pull that $100 bill and I try to go for a second one, I now have removed one of them. So I reduced down by 1 for the amount of $100 bills possible. But then I also decrease from 1 bill in the bag because I just took a bill out. And you just multiply. So you get 20. I see. We're going to actually reduce these fractions a little bit just to make it easier on those. 5 over 25 is 1/5 times 4 over 24, which is 1/6. That's going to be 1 over 30, which of course is going to be 3.3%-ish. Okay. And so what ended up happening here, right? Again, I would really love some extra colors, but I don't have them for whatever reason. I don't know. It's just kind of weird. But we're rolling with it, I guess. But the reason why I put this arrow here, we're just going to write denominator changed because a bill was taken out. And just again, to reiterate, this is going to be dependent because I took a bill out and I'm not putting that bill back in. Right, so I'm effectively changing the odds of getting another bill, whichever bill I'm looking for. Okay, next problem here. I'm going to go ahead and try to do this problem with you, but you can definitely follow along. But here, I'm looking to make a different kind of problem happen. And this would have been in your class. You would have had this problem in your class and it would make a little bit more sense. But let's say we had a class of, I don't know, let's say 12 women, 12 girls, whatever, right? And we had 10 guys, right, are in the class. 2 people are randomly chosen from the class to serve as a grader and a tutor. Find the probability that both events A and event B will be chosen. Okay. And so whenever we're looking at a problem like this, right, we want the grader to be a man. Okay. And this is kind of the same thing of like being randomly chosen, right? Imagine we had gotten that $100 bill in that bag. The same thing here, right? We still have this probability of A and B, but because I'm being able to choose a person out of like out of a hat, kind of the same idea as the last one, I'm going to say, well, that's going to be equal to the same probability of A times A, sorry, A times probability of B given A. Okay. So we'll go ahead and fill this in. If we're looking for our grader to be a man, we're gonna have 10 over 22, because 22 is the amount of students that we have, times. Now in this case, I have a woman as my tutor. The amount of women did not change. However, the amount of students in the class who have not been chosen have changed. Okay, and so we're gonna roll with this. I'm trying to see if we can simplify. We can a little bit, make things easier on ourselves. So we get 5 and 11 times 4 and 7, which is going to give us 20 and 77, which is definitely not reducible by any number that I can think of at this moment. And that fraction is probably about 26% or something like that. Okay. If I really wanted to, I could see it. Let's see. What is it? 20 divided by 77. Oh, I was close. It's approximately 25.97%. Yeah, I was pretty close. Okay. We keep moving on. At a school, 60% of students buy a school lunch. Only 10% of students buy lunch and dessert. What is the probability that a student buys lunch given that they buy dessert? Okay, so this one's going to look a little interesting, right? In this problem, we're already given event A. Event A is this one. But then we're told only 10% buy lunch and dessert. Well, again, right, we're seeing this word and, right, or both, right, kind of thing like that. And that's going to be event A, event A and B. Okay, where B is dessert. And so finally, what we're going to say this last sentence is, what does the probability look like for our B given A, right? So if we're told that 60% of students are buying a school lunch, then 10% are buying a lunch and a dessert. But how many students are actually buying dessert given that they are buying a lunch? Okay, I know it's a little confusing, but you'll see where all these kind of mash up together and whatnot in the next couple problems. But let's see how the setup is. So we have P, probability of A and B, equals the probability of A times the probability of B given A. So realistically speaking, we're just doing this problem, but just kind of backwards a little bit. Right, we're given P and B, whereas here we're solving for P and B. Or sorry, for A and B. Here we're given A and B, we're given A, we're looking for B given A. And that's what we're gonna do here. So it says P, probability of A and B happening, is gonna be 0.1. The probability of 0.8 or probability of A happening is 0.6. We're trying to figure out this X value here for our probability of B given A. So solve it just like normally, right? Get this 0.6 out of it here, right? Our X is then going to equal 1/6, or it's going to be 16.7%. Of course, that's going to be rounded a little bit. That's okay. We're going to take the exact same approach in this next problem. Okay, try it on your own first. Then you can come on back. This is going to be our P of A, right? The customers who buy pants, or sorry, pants. Then only 25% or 20% of customers buy pants and a belt. So P probability of A and B. And what we're looking for is those people who are buying pants or buying a belt because they bought pants, essentially. That's going to be our P. Oops. Oh, that works. is going to be our probability of B given A. Okay, so set it up. Probability of, oops, I set it up, right? Probability of A and B equals the probability of A times the probability of B given A. And you'll do all that. So we already told that 75% of people are going to buy pants. So that's going to be on the right-hand side. 20%, so 0.2. 75 here. For the X, divide by 0.75. 75. We are going to get X equals to 4 over 15. Which of course is going to be 26 seconds squared. Okay, very nice. We do end up having one more key point here. I think it's the last key point. Yeah, for sure, last key point. We have now our 11.3 section where we're talking about disjoint and overlapping events. And so we can call disjoint events mutually exclusive events. So basically events that happen at the same time, possibly, but are not going to interact with each other at all. Okay, when they have no particular outcomes in common. However, with the overlapping, that's whenever two possibilities can happen at the same time, right? More than one outcome is happening at the same time. And so here, right, we're looking at example 4. A 6-sided die is rolled. Draw a Venn diagram that relates the two events, then decide whether the events are disjoint or overlapping. Okay, so for our Venn diagram here, we're going to start with event A. Event A is here, then event B is here. In event A, we're looking for a 2 and a 4. So 2 and 4 goes here for sure. We don't know if it's going to be in the middle yet because we haven't looked at the right-hand side yet for event B. But event B says the result is an odd number. There's only 3 odd numbers, 1, 3, and 5. And because there is nothing in the middle here, this is going to be a disjoint. Disjoint events. Okay, so disjoint. You can keep going. In this problem, it says the result is an even number. So 2, 4, and 6. That is our event A. And then our event B. Okay. Event B says the result is a prime number. Okay, so hold on, let me clarify some things. 1, the number 1 is not a prime number. Or actually, even before that, I'm looking at my notes again. Sorry. One thing I wanted to put in here is that, right, we have our 2 options, our 2 and a 4, and our 1, 3, and 5 on our events, but 6 is actually on the outside because it's neither one of those 2 events. So I just want to put that out there. Okay. So because now we know this, I can go into my next point here, right? If I look at this, first off, let me just clarify, right? 1, the number 1 is not a prime number. Okay, so the 1 is going to be out here. Okay, there's not the number 1 is not a prime number. Okay, just understand that. Okay. And so a lot of us are going to think, well, I know 3 and 5 for sure are prime numbers. But actually, there's another prime number that we don't know of, or some of us might not know of. And that's actually going to be the number 2. Okay, so if I have 2 here on event B side, and I have a 2 here on event A side, I'm going to erase these and put it in the middle. And because that is in the middle now, this is going to be an overlapping. Overlap event. Okay, it's overlap because 2 is an even number and it is a prime number. Okay. Example 5, a card is randomly selected from a standard deck of 52 playing cards. What is the probability that it is a 10 or a face card? Okay, now here is where it gets a little bit trickier, possibly, right? When it says the word or, okay, you want to think of addition. And when I say addition, I'm saying that we're going to have some possibilities of our disjoint. Okay, so this is a disjoint because I'm looking at 10 and I'm looking at face cards. Well, 10s are not a face card, and a face card is not a 10, right? Obviously speaking, right? They're not the same number. They're not the same. Representation of each other. So this is going to be a disjoint. You can even see on the right hand side. They don't have any overlap at all. So this is a just disjoint event. And so for disjoint events, we have to write probability of A or B. And what that's going to do for us is going to be probability of A plus the probability of B. And you go from there. Well, the probability of getting a 10 is going to be 4 out of 52. The probability of getting a face card is going to be 12 out of 52. And that's going to equal 16 over 52. That is going to equal 4 over 13, which that, of course, equals 30.8%. Just like that. Pretty cool, right? We'll keep going. At high school swim meet, you and your friend are competing in the 50 miles, or 50 full swim meet is 50 miles. Wow. I'm pretty sure it's supposed to say 50-meter freestyle event. You estimate that there is a 40% chance that you will win and a 35% chance your friend will win. What is the probability that you or your friend will win the 50-meter freestyle event? Okay, because we have this or, we are going to be adding. So we're looking for the probability of A or B, given that the probability of A plus the probability of B, like so. Well, if 40% is event 1 or event A, and 35% is event B, we'll replace those values. 0.4 plus 0.35 has some easy math, 0.75, or 75% chance that either event A or B will be occurring. Okay? I think that's pretty simple enough. At least I hope so. But another thing that kind of really tells us off that we're going to be using the disjoint equation here is that you both can't win. Right? Since you both can't win, and there's only one winner, you can't have that 40% be in your favor, and you can't have that 35% be in their favor, assuming that the other one were to win. But we'll keep going. Okay. A card is randomly selected from a standard deck of 52 playing cards. What is the probability that it is a face card or a spade? Okay, now this is where we're overlapping. Okay, and whenever we overlap, it's still going to have that P, A, or B, right? And of course, you can look on with your reference sheet if you have it handy in front of you, which a lot of us are probably going to have to do, or probably going to have one in front of us. But if they're going to overlap, right, we don't want to account for all of the face cards, right? Because the face cards is event A. But then the spade is going to be event B. So if I'm going to account for P of A and P of B, knowing that there's some amount of overlap, I then have to take away, so subtraction, the probability of A and, okay, and you'll see what I'm talking about in a little bit. And we'll use the diagram to help us out. If we're looking for a face card, you're talking about all the face cards for the diamonds, the hearts, the spades, the clovers, or the clubs, whatever you want to call them. And that's 12 possibilities out of 52. Okay. But then if you want to incorporate every single possible spade here, there are 13 spades inside of a deck of 52 cards. But then because you're looking at face cards, because you're looking at spades, you have to then take away the overlap. In this case, we can see it, it's already here. 3. And that's what we're going to do. We're going to take 3 away. Like so. And then we're just going to combine like terms. We get 12 plus 13 is 25, minus 3 is going to be 22. 22 over 52. It's very nice. Which is going to equal 11 over 26. Which is then going to equal our 42.3%. Just like so. And that's it. So that's how you take care of overlap in a probability setting. Pretty easy, I think. Then we have an extra example 6 here. This case, you're going to roll a 6-sided die. What is the probability that you roll an even number or a number greater than 3? Okay, so in this problem, you're going to, I think probably the best way to do it would be a Venn diagram. But it's kind of whatever you want to do, whatever you think is easier for yourself. But the probability you roll an even number, so even A is arithmetic, and then a number greater than 3, that's going to be our bit B, bit B. And we still have this or, so it's going to be disjoint, oops, disjoint or overlapping. So event A is going to be all the even numbers, so 2, no, I was about to say 3, 4, and 6. And a number greater than 3 is going to be 4, 5, and 6, which of course they both share 4 and 5. So we have to put that, or sorry, 4 and 6, we have to put those in the middle like so. And so if I set up my problem, right, this is an overlapping problem now, A or B. That's going to be the probability of A happening plus the probability of B happening, just twice, minus the overlap between the two people. So the probability of A was 3 out of 6, plus the probability of B, which was also 3 over 6, minus the overlap between the two of them, which is 2 out of 6, like so. And so we are going to get 4 over 6, which is equal to 67%. Just like so. Okay. Just a reminder that that star up there on the left-hand side does mean that this is going to be tested. So make sure that you are aware of that. Make sure that you can perform and do these kinds of problems. Okay, because you will see it on the next quiz. Next, I want you to kind of think about this on your own. Go ahead and make some pretty good examples for me so that I can come back next week to see what you're looking at. But make sure you do one, because I think it'd be cool. It'd be really interesting to see how similarly we think or how differently we think and whatnot. Next, now this is going to be another problem that you're going to see on your exam, or sorry, on your test, quiz, whatever you want to call it. Okay. It says here, out of 200 students in a senior class, this is telling you a total. Okay, a total. It says 113 students are either varsity athletes or on the honor roll. This is your or statement, your disjoint and your overlap. But in this case, this is overlap because it says it's both, or sorry, it's either or. So it's you know what I'm trying to say. Sorry, I'm making that a lot more confusing. But this is your or. Okay, this is your P probability of A or B. Okay, so we're going to start there. Then there are 74 seniors who are varsity athletes and 71 seniors who are on the honor roll. Well, this is going to be our event B, so P of B. Then the 74 part, that's going to be our P of A because that was our first event. And we're going to use the exact same equation that we used beforehand, the overlapping equation, to help us out here. So we know that that we have P of A or B equal the P of A plus P of B minus probability of A and B. Okay. However, in this instance, we don't know what P and B is. So we had to figure that out. But we do know everything else. So P or B is 113 out of 200 students equals P of A, which is 74 students out of a possible 200, plus P of B, which is 51 over 200. And we're still trying to figure out this X. Now, just so that we're not confused, right, we're putting them over 200 because remember, probability is only from 0 to 1. It's never greater or any less. So make sure you're doing this correctly. Okay. So first, we're going to combine like terms. We're going to get 125 over 200 minus X, like so. Then we're going to subtract the 125 over 200 on both sides. We're going to get negative 12 over 200 equals of negative X. Don't be afraid here yet, because we can still divide out this negative. We are going to get X equal 12 over 200, which is equal to 3 over 50, or 6%. That's it. Go ahead and do the next problem. Try it on your own first. It's very similar to this one. Don't know why this is being finicky with me. But these are very similar questions. So go ahead and label it up and whatnot, and then come on back. We have a total of 45 paying customers. We have 42 of our or statements. So or are either of those two words are really going to trigger us into thinking our ors. So this is our P of A O B. There were 30 customers who bought orange juice. That's our P of A. Then 40 customers who bought our coffee. That's going to be P of B. Okay. Now, I know in the top part here, I say P of A or B, and it says coffee or orange juice in that order. And I just flipped them here. It kind of doesn't really matter because you're still working it the same way. But if you would prefer it to be in line and whatnot, you can go ahead and change these to a B or an A, right? But again, it doesn't really matter. But I can understand where people would prefer that and whatnot. Okay. Well, we're going to have P of A or B equal P of A plus P of B minus P of A and B. And of course, we know a lot of this information already. We know 42 out of 45 bought either coffee or orange juice. We said that coffee buying was the first event, so we'll say 40 over 45. Then the next set is 30 over 45 because that's the customers that are buying our coffee, or sorry, our orange juice. And we're going to subtract our X here. Keep going. Combine like terms, we get 42 over 45. And we get 70 over 45 minus X. Subtract on both sides, we get negative 28 over 45 equals negative X. And X is going to equal 25 over 28 over 45. Or that's going to be equal to 62%. And that is going to do it. That is our last part for Unit 11, Sections 2 and 3. I hope that was very informative, and I hope that you all complete this assignment and whatnot while I'm away. Okay, so make sure that you complete all the assignments and whatnot. But if you have any questions, you can message me. I can get back to you as soon as I can. If not, then I hope you have a good rest of your day, and I will talk to you all later. Bye-bye.